You did diazonium. What is that? NaNO2 and ACl. Make diazonium, and then you reacted it with phosphoric acid, H3PO2. Yeah, you took the amine off. You just used the amine to direct the bromines. Yeah. Otherwise, you wouldn't be able to do that. If you just try to react benzene with 3 equivalents of bromine, the first one's going to go here, the next one's going to go ortho to that, or para. They're not going to be meta to relationship. So this is an example of where you would use a sort of a protecting group or a group where you put it on and later take it off. Question?
I just did a mechanism where I used 3 equivalents of nitric acid, and then I did diazonium, and then I went to BRs. Is that okay? You do the same thing.
Okay. I think there's another way. You trinitrated.
Yeah.
Trinitrated. You're going retrosynthesis. Okay, you could trinitrate and they would all go meta. Okay, yeah, I never really thought about that. I always just show this. Then you reduce, you have the triamino with all of them being meta. And then you did diazonium on all of those and you converted them all to bromines. Yeah, that theoretically works. Problem is, trinitrobenzene is difficult to make because you put a deactivating group on, then you're trying to put another deactivating group on. Also, trinitrobenzene is explosive. Trinitrotoluene is, TNT. Trinitrobenzene is actually more explosive because it has lower carbon content. Higher nitrogen content, more explosive typically. So you got to be careful making trinitrobenzene. You may be. But on paper it works. Good, so yeah. The way I showed though, use the old tricky put it on, take it off route. The phosphinic acid. You can also do that. There's one in the workbook about making propofol. Propofol is is anesthetic, where the sulfonic acid is used to sort of block the pair position, so you only get groups ortho, and then the sulfonic acid is removed. Propofol is a common anesthetic used in some hospital settings. It's also the drug that killed Michael Jackson, basically. The milky. Propofol being very, some of these molecules aren't that big. Propofol, okay? You take phenol and you put these 2 groups on. But why didn't you go para? Because when you do it, you have the sulfonic acid here. And then you put the 2 groups on here, and then you remove the sulfonic acid because it can be removed to get a propofol. And the IV, is this soluble in water, yes or no? Well, it does have an OH, but it's not soluble in water. It's too much carbon, not soluble in water. And so when you make the IV, it really doesn't dissolve, and it looks milky. Okay? Now you could make the anion, and it would be soluble in water. The problem is, anions and phenols are fairly basic, and an IV of this, it'll cause necrosis at the injection site. So it's too basic. So it has to be given as the neutral. But the neutral is not that soluble, so it looks like milk. It's not completely dissolved. A suspension, more like a colloidal milk. Because it's not solid, it's just milky. Okay, we have a handout for the next material. I'll split it in half. One handout, two stacks. Any last questions about test 2 material? Test on Friday. Questions?
Could you do number 5 on page 30?
On page what?
30.
Is the answer not in the back?
It's one of the multiple choice, so.
Which of the following compounds is nitrated most rapidly? Number 5 on page 30. Nitrated most rapidly. Basically, we're looking at activating effects. Most rapidly. Okay, what type of activator deactivator is this? Strong deactivator. How about this?
3.
Weak deactivator. So bromobenzene would nitrate faster than this. But is that the fastest? How about this guy?
Trick question. Trick question though.
Okay, this question is a little bit, it depends on what the person asking wants it. It's a strong activator, but what type of conditions are we under? Very acidic. This is going to be protonated. And when it's protonated, it's a strong deactivator. Now, some people will say this is the answer and not consider this point. What about this guy? That's not a standard functional group there. How would you evaluate that? Activator, deactivator? It's a carbon, but it does have 3 chlorines on it. Do we have dipole? Would you consider that atom an electron poor? Yes. Because if it's electron poor and doesn't have a lone pair, then it's what? Strong deactivator. Indeed, it's considered a strong deactivator because it's electron poor and doesn't have a lone pair. So, if all these are strong deactivators, which one's the most activated? This one. It's not really activated, but it's just not as worse as the other 3. Did I get the right answer?
Yes.
Okay. I'm wondering if this was listed as the right answer. It all depends on if the question here is considering that it's being protonated. Is that what you were asking about?
Yeah, because I thought it would be A because it was group 1 versus group 3.
It's under strongly acidic conditions, though. Now, actually, you can look in the literature. If you have concentrated sulfuric acid, you got problems. If you keep it dilute, it will act as a activating group, orthopair. See, but I've set it up to where you just. Also, this is homework, okay? So you can ask and you can learn. I'm considering it strong enough to protonate and make it a deactivating group. Mark?
Would not react at all with the acidic conditions? Because I was running with your main hydrochloric acid.
No, you're not going to react with the acid. It's just this carbon is electron poor. Okay. The handout is coming around for our next other questions. Yes.
Number 1.
Oh, where? This here?
Is D not aromatic?
B?
D.
D? Which finds is aromatic?
But look at how small it is.
But 5 plus 2
Hold on, I think you're. Is the answer B? Yeah, I think D. D is in dog. Is aromatic.
But wouldn't
Yeah,
be
it
too
is.
small though?
Yeah. 2 pi electron. 4n plus 2, we're in is 0. Yes, that's wrong. Both B and D are aromatic.
Wouldn't it be too small though? To fully.
Yes, good catch there.
It's too small. There's no way it's set equally out on the triangle.
I'll correct that. Sorry about that.
Yeah, it's small.
to be
Yeah.
Question?
But like a normal question that was real class, but I didn't understand like how you get rid of the
What page?
page 26.
I suspect I know which one you're talking about. Two butyl group or something?
I know, I don't understand it though. Yeah, I don't understand it.
Page 26. A couple interesting mechanisms there, like that one there. No answers implied here. You basically need this cation. This is going to complex. When this ionizes off, you get what? You get this cation. Can you not give a mechanism from going from here to here? How do you make oxygen a better leaving group? Protonated, and it makes the oxygen become charged. What charge? Positive charge oxygen is a good leaving group. Okay? Because if the oxygen, when it leaves, it gets to take the lone pair with it, and it owns the lone pair. Well, if this carbon just leaves, what does that give? It gives that, which we need to make this, plus what? It's a double bond O with a carbon. And a lone pair. Because these electrons move on to carbon as a lone pair. What's the charge of the carbon here?
Way too unstable though.
What's the charge of the carbon?
Way too unstable.
Neutral. That's it. Now that's a poor resonance structure because the carbon doesn't have an octet. 2, 2, 4, 6. We can move these electrons down, and if you want to show the this lone pair here, but now this has charges. What's the charge of the carbon now? Negative. What's the charge here? Positive. This is the resonance structure. Now, your choice. Which do you like best? Do you like carbon having an octet, or do you like carbon having no charge?
Carbon having an octet.
It's a toss-up. Basically, this is two structures for the same thing. What is that? That's neutral CO. We call it carbon monoxide. Yes. It just loses carbon monoxide to make the.
Oh, so you just like ionize.
First off, you have to. But look, when that left to make carbon monoxide, which is a neutral molecule, it formed a tertiary carbocation. Those are easy to form.
But isn't it more likely that the double bond would just attack the positive charge to create?
You mean here?
Yeah.
Maybe this ionizes so fast that it can't.
It
It doesn't have time. It just, as soon as it, boom, it's just gone and this attacks this.
Okay.
There's a known reaction. There's the carbon monoxide right there. I mean, CO. This is neutral, right? I mean, unless a charge is shown. So that's neutral. That's carbon monoxide. There's your carbon monoxide. If you know the structure, if you started with this and say, well, how am I going to make that? You would have to just do this to make it. But that gives you also the cation you need for the ring to attack. That's a known reaction. This doesn't happen unless there's a tertiary carbon over here, most likely. If it was primary secondary, it would just stay here. But things are driven by entropy. This molecule turns into 2. Entropy is very powerful. As long as you got something going for it. You produce a neutral molecule and you form a nice tertiary cation. Of course, this was pretty stable too. But apparently it still will decompose and break into carbon monoxide. Question?
Wouldn't you have Goderman on the that reaction?
Have what on it?
Goderman, because you have CO and ACO, right? So it,
This could produce.
yeah. So wouldn't you not have that after it just takes a benzene and forms a?
You're saying you might start getting some aldehyde form?
Yeah.
Possibly.
Wouldn't that
You'd have to look up
be, okay.
how the reaction's done. If any of that side product is actually formed in this reaction.
Okay.
Sounds like you're making an informed evaluation of the reaction. It's good. Good. That's how chemistry's done. You have informed, you evaluate, and ask questions, and then here's how you get your answer. You got to go to lab. Mother Nature's a wildly crazy lady. It may give you a significant side product. Before we move on to new stuff, I wanted to show you something. What's an allotrope? What's an allotrope?
Different form of carbon.
It's like allotropes of carbon. You have charcoal, graphite, diamond. Those are all allotropes of carbon. Graphene, which is newest. Okay. Diamond is where the carbons are. It's all carbon with but they're all tetrahedral bonded. Polymers, I mean, it's all just repeating carbon, carbon, carbon. There's no other elements involved. So it's tetrahedral, and this would be a unit cell. Okay? In graphite, instead of them being bonded tetrahedrally, they're actually benzene rings. So they're sp2. And it's just one benzene ring after another. If you have hexagonal tiles in your bathroom, you can look at this. Tile, tile, tile. They're all just there. Okay? And here's a flat, just array. This is a big old sheet. Okay? But because it's planar, then you can have another one and they can just stack. And actually, pi electrons really like to interact because they're very polarizable. And so they have good van der Waals attractions. Now, in the past few years, what have we got? Graphene. That's where you take graphite and you separate one layer of. And graphene actually has some very amazing properties. You all talked about graphene before somewhere?
I just private research. I've been looking at it. They've been doing what
It's really strong.
I'll do what?
they're trying to do
Graphene.
Yeah, those electrolytes.
Graphene. Actually, graphene was first originated when someone took Scotch tape and just peeled off some of the graphite. You can read about it. Look up graphene. It's amazing information. You ever heard of Wikipedia? Yeah. I use it all the time. You get great information. But just like anything, you always have to have some skepticism when you read, no matter what. Even my handouts, right? Okay? So there you go. Lots of benzene rings, allotrope of carbon, diamond, yeah. Tetrahedral nature.
Is that tetrahedral nature versus the increased stability from the benzene rings the reason why diamonds will slowly convert back and break down and then graphite?
Oh, diamonds are forever.
Well, but they're not.
I reckon you're thinking out long term.
Very, very long.
Let's look at new material. Okay, next topic. Dr. Chem. Okay, test 3 and test 4 are mainly over carbonyl chemistry. Okay? Functional groups with carbonyls. Question?
Sorry, I had one last question on the test. If you have zinc HCl, can that reduce a ketone?
Usually you have to include the mercury.
Okay, so if you want to selectively reduce like a nitrogen, could you use like zinc HCl or HCl?
It can be difficult if you just want to reduce the nitro, because any way you do it, you're going to, I don't know. If you just use zinc HCl, will it also reduce the ketone? I'm not sure. I'm suspicious that it would or would not. I don't know. Traditionally, you need the mercury. So if you say you need the mercury, then it should be selective. You should not do it without the mercury. I'm just going to do a little more research and see. Now, there's lots of other ways to reduce nitro groups, so I'm sure there's a way to do it selectively. Okay, test 3 and 4 are mainly carbonyl chemistry, compounds with carbonyl groups. Test 3 is largely acid derivatives, carboxylic acids and derivatives of that. Test 4 is largely aldehydes and ketones. Okay? Carbonyl chemistry is very important, particularly for going on to biochemistry. Here are some carboxylic acids and derivatives. Lots of drugs, but we see carboxylic acid, Zyrtec. What do we have here? Another carboxylic acid, Allegra. Ester, so remember your functional groups. Ester. Amides. Amides, including in Lipitor. Lipitor, of course, also has the parole ring here. Lipitor is a nice little compound. Aromatic rings, para-substituted fluorine group, some chiral alcohols, carboxylic acid, amide, isopropyl group. Nitrile does not have a carbonyl, but it's still considered an acid derivative. Okay? Why are these all considered acid derivatives? Because they're all the same oxidation state as the carboxylic acid. They all come from the acid without doing redox chemistry. Look at the carboxylic acid, the carbon. How many bonds to a more electronegative atom? 3. 3 bonds to a more electronegative atom. 2, 1, 3. 3. Amide. How many bonds to a more electronegative atom? 3. Ester. How many bonds to a more electronegative atom? 3. Nitrile. How many bonds to a more electronegative atom? 3. You see how it's okay. It's at the same oxidation state in terms of that type of definition. Aldehydes and ketones. Just look at this ketone, right? How many bonds to a more electronegative atom? Only
2.
Only 2. It's not the same. You have to do redox chemistry to get to this from one of those. So it's not considered an acid derivative. Okay, nomenclature, acid derivatives. Carboxylic acid, longest continuous chain, with the carbonyl of the acid being in one position always. Longest continuous chain is 4. That's like butane. We replace the E with oic acid. So it becomes 2 words. So this molecule here is known as butanoic acid. Replace the E with oic acid. Pretty straightforward. Name this compound here. Longest continuous chain. 1, 2, 3, 4, 5, 6, 7, 8. No. Carbonyl is part of the longest continuous chain. It's the one position, so that's not it. Start there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 6. So it's hex. Remove the E. Hexanoic acid. But what's on the hexanoic acid? This group is at what position?
2.
The 2 position. So we have a 2 what? 2 propyl. It's all one word. 2 propyl hexanoic acid. So this guy is commonly known as acetic acid. Now, if you named it by IUPAC, it would be named what? Longest continuous chain. 1, 2. What would you call that? Ethanoic acid? Ethanoic acid? Nobody calls it ethanoic acid. It's called acetic acid. Okay? Longest continuous chain. This is 1 carbon. Methanoic acid? Nobody calls it methanoic acid. Formic acid. Certainly acetic acid is very common. You have your amino acids you'll learn in biochem if you're not already learning them in biology. These are really alpha amino acids because the first carbon is often denoted as alpha. And the second would be beta down the line. So at the alpha we have the amine, alpha amino acids. But these are your protein building blocks, like glycine and alanine and serine and threonine. Right, you know those? Name of this guy. 1, 2, 3, 4. Butanoic acid. What's on the butanoic acid? 4-hydroxybutanoic acid. But if you do it alpha beta, gamma. It's also known as gamma hydroxybutanoic acid. And what is GHB?
Like anti something. It's like
known as date rape
narcolepsy.
drug.
Yeah.
It's a hypnotic. GHB. Okay? But that's what GHB stands for. Gamma hydroxybutanoic fairly small molecule, but it has hypnotic properties. Okay.
Wait.
Esters. Esters are going to have two components. You have the kind of the acid component, the carbonyl component, and then you have the R group. Okay? Because that's an acid with an H, but if we put an R group on, it becomes an ester. You name it with two names. You name the carbonyl portion, or the kind of the acid portion, 1, 2, 3, 4. Instead of butanoate, it's O8. I'm sorry, instead of butanoate, it's butanoate. So does it say we're replacing the E? We're replacing the E of butane with O8. And then we name the R group separately, and that's just an ethyl. So this molecule is ethyl butanoate. In terms of numbering, this is 1, 2, 3, 4, just like you would expect for the carbonyl portion. For the R group, the carbon bonded to the oxygen is the 1 position. And it goes out from there.
Butanoate counts the second oxygen, correct?
Butanoate,
Yeah.
1, 2, 3, 4.
I mean, so is the second oxygen between the ethyl and the butanoate not considered to be part of either group then? Oxygen on the right? That's part of ester. Yeah.
I should have maybe done it like this instead of. I mean, that's the original acid portion that we put R group on. Name these two here. We're probably going to be out of time. Please name those. Let me make some miscellaneous comments. Okay, please name these. Okay, acetic acid. The anion is called what? The anion of acetic acid is called what?
Huh?
Okay, you should have learned this in Gen Chem. It's called what? Thank you. Acetate. Acetate. Okay? So this is what? Sodium acetate. Okay? Of course, that's ionic, right? Potassium acetate. Magnesium acetate. Strontium acetate. Whatever acetate you want. That's acetate. Okay? Now, if you put an ethyl on here, which is covalent, that's called ethyl acetate. This is covalent, though, with the ethyl group. So it's ethyl acetate, like ethyl butanoate, but it's not called ethyl ethanoate. Ethanoate is not called ethanoate, it's called acetate. So do know that. And ethyl acetate is usually abbreviated like this, because that's ethyl, and acetate is like that, and that's minus. If it's just acetate, that's acetate, because that's OA-Sil. That's an acyl group with an oxygen, OA-Sil. Anion? Okay, it's all there. But you should know acetate. That's on Friday. We'll be going at the top of the hour. Okay. Have a good day, guys. See some of you.